A non-standard C-infinity structure on R, part 1 of 3. Why isn't topology enough? This video in 3 parts proves that the map phi of S equals S cubed defines a C-infinity differentiable structure on R. That structure is distinct from the standard one. Part 1 establishes the motivating question and verifies that phi is a homeomorphism, which is the first step in constructing the atlas. A homeomorphism between two topological spaces is a continuous bijection whose inverse is also continuous. This is the standard criterion for saying that two spaces have identical topological structure. The real line R can be given coordinates in many ways. The standard one assigns to each point x the coordinate x itself, but one could equally assign to a point S the coordinate s cubed, a nonlinear reparametrization. The central question is whether two coordinate systems on R can both be homeomorphisms, so that topology cannot distinguish them. Can they nonetheless give fundamentally different notions of which functions count as smooth? This is the question that forces us beyond topology and into the theory of differentiable structure. Before answering it, we fix precisely what smoothness means. That is, what it means for a function to be C-infinity. A function from R to R is called smooth, or C-infinity, if every derivative of every order exists at every point. Formally, f prime, f double prime, f triple prime, and so on must all exist and be finite everywhere on R. Every polynomial is smooth in this sense, because polynomial functions can be differentiated any number of times with no obstruction. In particular, s cubed is smooth. On the other hand, the function t to the 1/3 is continuous everywhere on R. Its derivative at t equals 0 does not exist as a finite number. The graph has a vertical tangent there, so it is not smooth. This distinction will be decisive. When we declare a coordinate map phi to be part of an atlas, we are making a specific claim. A function on R is smooth if and only if its expression in the coordinate phi is smooth. Choosing a different phi changes the criterion and therefore potentially the collection of functions that qualify as smooth. The specific pair of functions just named, s cubed and t to the 1/3, will reappear later. They are the two transition maps whose smoothness determines whether our two atlases are compatible. The map phi of S equals S cubed. Its graph rises steeply for large S and is flat near the origin, where the slope is exactly 0. At the origin, the derivative of S cubed is 3 times S squared, evaluated at S equals 0, which gives 0. The tangent line is horizontal. The slope is 0, finite and well-defined. The function S cubed is C-infinity. Every derivative of every order exists at every point, including the origin. Now consider the inverse map. Phi inverse of t equals t to the 1/3. The graph is defined on all of R, including negative t, where the real cube root of a negative number is negative. Both branches are shown. At the origin, the secant slope from 0 to a nearby point t equals t to the 1/3 divided by t, which is t to the negative 2/3. As t approaches 0, this quantity grows without bound. The tangent direction becomes vertical. The slope diverges to infinity. No finite derivative exists at 0. The function t to the 1/3 is continuous everywhere, but not differentiable at 0, so it is not C-infinity. Yet both maps are homeomorphisms from R to R. Each is continuous, bijective, and has a continuous inverse. Topology cannot distinguish them. The difference is visible only through the derivative, and that is precisely the information a differentiable structure is designed to capture. A homeomorphism preserves everything that can be stated in terms of open sets: convergence of sequences, continuity of functions, compactness, connectedness. But a homeomorphism does not preserve derivatives, curvature, or smoothness. Two spaces can be topologically identical while having completely different calculus on them. The map f of S equals S to the 1/3 is a homeomorphism from R to R. It is continuous, bijective, and its inverse S cubed is also continuous. But it is not differentiable at 0. Computing the difference quotient at 0 gives the limit of t to the negative 2/3 as t approaches 0, which diverges to positive infinity. No finite derivative exists at that point. Topology sees S to the 1/3 and the identity as equivalent maps. A differentiable structure sees them as fundamentally different. To do calculus, we must specify which coordinate systems are declared smooth, and that additional specification is exactly a differentiable structure. The graph of t to the 1/3 on R. Both branches are shown. The positive branch for t greater than 0 and the negative branch for t less than 0. The function is continuous everywhere on R, including at the origin. Fix the origin. Place a second point on the curve at t equals 1. The second line through the origin, and this second point has a slope equal to the ratio t to the 1/3 over t. This ratio equals t to the negative 2/3. The secant line is drawn from the origin to the moving point. At t equals 1, the slope is 1 to the negative 2/3, which equals 1. The slope readout confirms this. The difference quotient definition of the derivative at 0 is the limit of the slope as the moving point approaches the origin. As t decreases towards 0 from the right, the slope t to the negative 2/3 grows without bound. The secant line rotates continuously toward the vertical. There is no finite angle it approaches, the rotation continues without limit. From the left, approaching through negative t, the same divergence occurs by symmetry. The dashed vertical line marks the direction the secant is approaching. The secant is nearly indistinguishable from the vertical reference. The tangent direction at the origin, if it existed, would be exactly vertical. But a vertical line has no finite slope. The limit of the difference quotient does not exist as a real number. The conclusion is that f prime of 0 does not exist. The function t to the 1/3 is not differentiable at 0 and therefore not C infinity. This is the geometric content behind the algebraic divergence computed in the transition map check. A topological space is a set M together with a designated collection tau of subsets called open sets. These must satisfy three axioms. The empty set and all of M are open. Arbitrary unions of open sets are open, and finite intersections of open sets are open. These axioms capture exactly the properties needed to speak about convergence and continuity without reference to any metric. A map F from M to N is continuous if the preimage of every open set in N is open in M. Combined with a continuous inverse, this recovers the homeomorphism condition stated a moment ago. The two spaces are then topologically indistinguishable. Throughout this video, M equals R with its standard topology generated by open intervals. A homeomorphism from R to R is simply a continuous bijection with a continuous inverse. There is no further condition. A chart on M is then precisely a homeomorphism from an open subset of M into Euclidean space, which is what we examine next. A chart on a topological space M is a pair. It consists of an open set U in M, together with a homeomorphism phi from U onto an open subset of Rn. Geometrically, phi unrolls the patch U flat into Euclidean space, so that ordinary calculus, which is defined on Rn, can be performed there. When two charts overlap on a region, the composition phi beta, composed with phi alpha inverse, is a map between open subsets of Rn. This map translates between the two coordinate systems. This is the transition map. For functions on M to have a well-defined notion of smoothness, regardless of which chart we use, all transition maps must be C infinity. This is the compatibility condition that defines a C infinity atlas. With only one chart covering all of M, there are no overlapping patches, so no transition maps need to be checked at all. A single homeomorphism phi from M into Rn is sufficient to produce a C infinity atlas on M. The atlas in question is the singleton containing just the one chart, M and phi. The proof is immediate. The definition of a C infinity atlas requires that all transition maps between overlapping charts are C infinity. With only one chart in the atlas, the only transition map that can be formed is phi composed with phi inverse. This composition equals the identity on the image of phi. The identity is C infinity. There are no other transition maps to check. The compatibility condition is satisfied vacuously. This proposition is the key lever for the entire problem. To confirm that the atlas defined by phi of S equals S cubed is a valid C infinity atlas, we need only verify that S cubed is a homeomorphism. No transition map computation is required. The structure is guaranteed by the proposition the moment homeomorphism is confirmed. We now carry out that verification. To apply the single chart criterion, we must verify that phi of S equals S cubed is a homeomorphism from R to R. There are four things to check. First, phi is continuous. A polynomial is continuous everywhere on R, so this is immediate. Second, phi is injective. S cubed is a strictly increasing function. If S1 is less than S2, then S1 cubed is less than S2 cubed. Because of this, the map is injective. Third, phi is surjective. For any real number t, the real cube root t to the 1/3 is a well-defined real number, and phi of that quantity equals t. The real cube root exists for every real t, including negative t, because the cube root of a negative number is negative. Fourth, the inverse phi inverse of t equals t to the 1/3 is continuous on R. On the open set where t is positive, t to the 1/3 is a composition of continuous functions and is continuous there. On the open set where t is negative, the same holds by the formula negative of the absolute value of t raised to the 1/3 power. At 0, take any sequence t sub n converging to 0. The absolute value of t sub n to the 1/3 equals the absolute value of t sub n all raised to the 1/3 power. This quantity converges to 0 as t sub n converges to 0. So phi inverse is continuous at 0 as well, and therefore continuous on all of R. Therefore phi is a homeomorphism. By the single chart criterion, the atlas A phi, consisting of just the one chart R and phi, is a valid C-infinity atlas on R. Part 2 will ask whether this atlas is equivalent to the standard atlas AID, which uses the identity map as its single chart. Part 1 established 5 things. A C-infinity function is one whose derivatives of all orders exist everywhere. Polynomials satisfy this. T to the 1/3 does not. Homeomorphisms preserve topology, but not smoothness. A differentiable structure is the additional datum of which coordinate systems are declared C-infinity. A single chart covering all of M automatically forms a C-infinity atlas because the only transition map is the identity. And phi of S equals S cubed is a homeomorphism, so A phi is a valid C-infinity atlas. Part 2 will determine whether A phi and the standard atlas, AID, define the same differentiable structure. Part 2. When do two atlases define the same differentiable structure? We have two atlases on R, the standard one and the one defined by phi of S equals S cubed. This part computes the transition maps between them, determines whether those maps are C-infinity, and introduces the formal definitions of atlas equivalence and differentiable structure. The two atlases are AID, whose single chart is the identity map on R, and A phi, whose single chart is phi of S equals S cubed. Both are valid C-infinity atlases on R as established in Part 1. The question is whether these two atlases define the same C-infinity differentiable structure on R, or whether they define distinct ones. The answer will come in 3 steps. First, we compute the transition maps between the two atlases, then we check whether those transition maps are C-infinity, and finally, we formalize what it means for two atlases to define the same structure. An equivalence relation on a set S is a relation satisfying 3 properties. Reflexivity means every element is related to itself. Symmetry means that if A is related to B, then B is related to A. Transitivity means that if A is related to B and B is related to C, then A is related to C. The equivalence class of an element A is the set of all elements in S that are related to A. We will shortly define an equivalence relation on the set of all C-infinity atlases on R. The equivalence classes under this relation will be exactly the differentiable structures. Specifying a differentiable structure means choosing an equivalence class. This means declaring which collection of atlases we regard as defining the same smooth calculus without committing to any single representative atlas. To define that relation precisely, we first need the formal definitions of chart and atlas. Recall the chart definition from a moment ago. A chart is a pair U and psi, where U is an open subset of M and psi is a homeomorphism from U onto an open subset of Rn. With that in hand, the compatibility condition previewed there can now be stated precisely as a C-infinity atlas. A C-infinity atlas on M is a collection of charts whose domains together cover all of M, and for which every transition map is C-infinity. The transition map between two charts is the composition psi beta composed with psi alpha inverse. This map translates between coordinate systems on the overlap region U alpha intersect U beta. It goes between open subsets of Rn, so asking whether it is C-infinity is a question in ordinary calculus. We require transition maps to be C-infinity for a specific reason. We want the notion of a smooth function on M to be well defined, independently of which chart we use to test it. A function f from M to R is called smooth if its coordinate expression f composed with psi inverse is C infinity. For two charts to agree on which functions are smooth, the map converting between their coordinates, the transition map, must itself be C infinity. A manifold M with two overlapping coordinate patches. The patch U alpha is shown on the left and U beta on the right. Each patch is an open subset of M on which a chart is defined. The overlap U alpha intersect U beta is the region covered by both charts simultaneously. It is on this overlap that the transition map is defined. Each chart maps its patch homeomorphically into Rn. The chart psi alpha maps U alpha into the left disk and psi beta maps U beta into the right disk. All of calculus will take place inside these Euclidean disks. The image of the overlap region under each chart is highlighted inside the disks. Psi alpha maps U alpha intersect U beta to the shaded region in the left disk. Psi beta maps that same overlap to the shaded region in the right disk. These two shaded regions are the domain and codomain of the transition map. The transition map psi beta composed with psi alpha inverse goes horizontally between the two Euclidean disks. It first inverts psi alpha to return to M, then applies psi beta to land in the right disk. This composition is entirely a map between open subsets of Rn. The Atlas compatibility condition asks exactly one question about this horizontal arrow. Is it C infinity? If all transition maps between all pairs of overlapping charts are C infinity, the Atlas is valid. One map failing that test disqualifies the entire Atlas. To test whether the two atlases AID and A phi are equivalent, we check whether their union is itself a C infinity atlas. This union is the two-chart atlas containing both the identity chart and the phi chart. For the union to be a C infinity atlas, every transition map between the two charts must be C infinity. There are two non-trivial transition maps to examine, one in each direction. A single failure is sufficient to conclude that the union is not a C infinity atlas. The first transition map is tau 1 from the identity chart to the phi chart. It equals phi composed with the identity inverse, which is just phi. So tau 1 sends s to s cubed. The second transition map is tau 2 from the phi chart back to the identity chart. It equals the identity composed with phi inverse, which is phi inverse. So tau 2 sends t to the 1/3. Tau 1 s cubed is a polynomial and therefore smooth everywhere. Tau 2 t to the 1/3 is continuous everywhere, but we must check carefully whether it is differentiable at t equals 0. That check is the computation on the next slide. It is the single decisive calculation in the entire argument. To test whether the two atlases are compatible, we examine the union atlas containing both the identity chart and the phi chart. The question is whether that union is a C infinity atlas. The left box represents RID carrying the standard identity chart. The right box represents R phi carrying the phi chart. The center box labels the question. Is the union atlas C infinity? The first transition map tau 1 goes from RID to R phi. It is computed as phi composed with the identity inverse, which is just phi, so tau 1 sends s to s cubed. Tau 1 is a polynomial, hence C infinity everywhere. It passes the compatibility test. The second transition map tau 2 goes in the reverse direction, from R phi back to RID. It equals the identity composed with phi inverse, which is phi inverse. So tau 2 sends t to the 1/3. Tau 2 is not differentiable at t equals 0. The difference quotient at 0 equals the limit of t to the negative 2/3, which diverges. No finite derivative exists. Tau 2 fails. One failure is sufficient. A C infinity atlas requires every transition map to be C infinity. Because tau 2 fails, the union atlas is not C infinity. The two atlases are therefore inequivalent. They define distinct differentiable structures. To check whether tau 2 of t equals t to the 1/3 is differentiable at 0, compute the difference quotient. The derivative at 0 is the limit as t approaches 0 of the quantity f of t minus f of 0 divided by t minus 0. Since f of 0 is 0, this is the limit of t to the 1/3 divided by t, which equals the limit of t to the negative 2/3. From the right, as t approaches 0 through positive values, t to the negative 2/3 grows without bound to positive infinity. From the left, as t approaches 0 through negative values, t to the negative 2/3 is the reciprocal of the absolute value t to the 2/3. This quantity also grows without bound. Both one-sided limits diverge, so the limit does not exist as a finite real number. The function t to the 1/3 has no finite derivative at 0. Geometrically, the graph of y equals t to the 1/3 has a vertical tangent line at the origin. The slope becomes infinite. Compare this to the graph of y equals s cubed at s equals 0. It has a horizontal tangent with slope exactly 0, smooth in every sense. Topology treats both phi and phi inverse as equally good homeomorphisms. Smooth structure distinguishes them sharply. The formal consequence of this failure, that the two atlases are inequivalent and define distinct differentiable structures, is drawn out on the next slide. Two C-infinity atlases on M are equivalent if their union, the atlas obtained by pooling all charts from both, is itself a C-infinity atlas. Concretely, this means that every chart from the first atlas is C-infinity compatible with every chart from the second atlas, meaning all transition maps between them are C-infinity. A C-infinity differentiable structure on M is an equivalence class of C-infinity atlases under this relation. Equivalently, one can specify a differentiable structure by choosing the unique maximal C-infinity atlas in that equivalence class. This maximal atlas is obtained by taking every chart on M that is C-infinity compatible with any given atlas in the class. The existence of the maximal atlas follows from Zorn's lemma applied to the partial order of compatible C-infinity atlases ordered by inclusion. The key point is this: any two atlases representing the same differentiable structure share the same maximal extension. As a result, all questions about smoothness on M are independent of which representative atlas was written down. The computation of part 2 now tells us which equivalence class each of our two atlases belongs to. Consider the set of all C-infinity atlases on R. Each point inside this boundary represents one such atlas. The atlas equivalence relation partitions this set into disjoint equivalence classes. Two atlases are in the same class if and only if their union is a C-infinity atlas. Two distinct classes appear here. The standard atlas AID, consisting of the single chart given by the identity map, sits inside the left equivalence class. Many other atlases are equivalent to AID. Any atlas whose charts are all C-infinity compatible with the identity chart belongs to the same equivalence class. The atlas Phi, consisting of the single chart phi of S equals S cubed, sits in the right equivalence class. It shares that class with every other atlas compatible with phi. The dashed line between the two blobs is not a choice, it is a mathematical fact. The transition map tau 2 equals t to the 1/3 is not C-infinity at 0. Therefore, the union of any atlas from the left class with any atlas from the right class fails to be C-infinity. No chart from the left class is compatible with any chart from the right class. The partition is forced. Each equivalence class contains a unique maximal atlas, the atlas obtained by including every chart compatible with any member of the class. The two maximal atlases are distinct and do not intersect. A phi is not equivalent to a id. They define two different C-infinity differentiable structures on R. The second transition map tau 2 of t equals t to the 1/3 is not differentiable at t equals 0, as the computation on the previous slide showed. The atlas definition requires that every transition map between overlapping charts be C-infinity. Tau 2 fails this requirement. Therefore, the union of AID and A phi is not a C-infinity atlas. The formal consequence is as follows. Since the union of the two atlases is not C-infinity, the two atlases are inequivalent. They define distinct C-infinity differentiable structures on R. In terms of maximal atlases, there is no single maximal C-infinity atlas that contains both the identity chart and the phi chart as compatible members. Any atlas containing both would include the transition map t to the 1/3, which is not C-infinity at 0, a contradiction. The problem asked to prove that phi of S equals S cubed defines a structure different from the standard one. This is now established. Part 2 established 5 things. The transition map tau 1 equals S cubed is C-infinity, while tau 2 equals t to the 1/3 fails to be differentiable at 0. For a union of atlases to form a C-infinity atlas, Every transition map must be C infinity. One failure is enough to disqualify the union. Two atlases are equivalent if and only if their union is C infinity. A differentiable structure is an equivalence class of atlases, or equivalently the unique maximal atlas in that class, whose existence is guaranteed by Zorn's lemma. Consequently, Aid and A-phi are inequivalent and define two distinct C infinity differentiable structures on R. Part 3 will address a subtle but important further question. Are the two resulting smooth manifolds diffeomorphic to each other, even though their structures are inequivalent? Part 3. Different structure does not imply non-diffeomorphic. Part 2 showed that Aid and A-phi define distinct differentiable structures. Part 3 shows that the two resulting smooth manifolds are nonetheless diffeomorphic and explains precisely why this does not contradict Part 2. Part 2 showed that Aid and A-phi are inequivalent. Their union fails to be a C infinity atlas. Yet the map phi from R phi to RID, sending S to S cubed, turns out to be a diffeomorphism between the two smooth manifolds. The resolution to the apparent contradiction is that these are two logically independent statements. Saying the structures are different means there is no single C infinity atlas containing both the identity chart and the phi chart simultaneously. Saying the manifolds are diffeomorphic means there exists a smooth bijection with a smooth inverse between them. Smoothness here is tested through each manifold's own coordinate charts, not through any combined atlas. The computation for diffeomorphism is entirely different from the computation for atlas compatibility. To make this precise, we first fix the definition of a smooth map and of a diffeomorphism. A map F from a smooth manifold M to a smooth manifold N is called smooth under one condition. Take any chart psi on M and any chart chi on N and form the composition chi composed with F composed with psi inverse. The coordinate representative of F is smooth if this coordinate representative is C infinity as a map between open subsets of Euclidean space. This is the only way to define smoothness on manifolds, always through coordinate charts. A diffeomorphism is a smooth bijection whose inverse is also smooth. Two smooth manifolds are diffeomorphic if there exists a diffeomorphism between them. The critical point for this problem is that when each manifold carries exactly one chart, there is exactly one coordinate representative to compute for each of F and F inverse. The computation is therefore fully explicit, and we will see that both representatives reduce to the identity. The next slide fixes the specific map F and writes down the two coordinate representatives to be computed. We denote by R phi the real line equipped with the smooth structure given by the atlas A phi. This atlas consists of the single chart phi of S equals S cubed. We denote by RID the real line equipped with the standard smooth structure given by the atlas AID, consisting of the single chart, the identity. The claim is that F equals phi, the map sending S to S cubed, is a diffeomorphism from R phi to RID. To verify this, we compute the coordinate representative of F and the coordinate representative of F inverse. For F, going from R phi to RID, the source chart is phi and the target chart is the identity. The coordinate representative is identity composed with F composed with phi inverse. For F inverse, going from RID to R phi, the source chart is the identity and the target chart is phi. The coordinate representative is phi composed with F inverse composed with the identity inverse. Both computations are carried out on the following slides. Compute the coordinate representative of F in the forward direction. F equals phi. So the representative is the identity composed with phi inverse. The two phi's cancel. Phi composed with phi inverse equals the identity on R. Composing with the identity on the left changes nothing. The result is the identity map on R. The identity map on R is C infinity, therefore F is smooth as a map from R phi to RID. The reason phi inverse does not cause the same problem here as it did in part 2 is the following. In the transition map computation, phi inverse appeared as a standalone function to be differentiated. It was the map from the phi chart back to the identity chart, and the cube root function sat there unprotected. Here, phi inverse appears first as the source chart, and then phi appears immediately as F itself. The two cancel before any differentiation is performed. The cube root is completely absorbed by the composition. The same cancellation mechanism applies in the reverse direction. The coordinate representative of F is the composition, target chart, then F itself, then source chart inverse. With source chart phi and target chart the identity, this gives the identity composed with F composed with phi inverse. Since F equals phi, the chain reads phi inverse, then phi, then the identity. The first two boxes, phi inverse and F equals phi, sit adjacent in the chain. Phi inverse followed immediately by phi is the composition phi composed with phi inverse, which equals the identity on R. The cancellation is complete. The pair phi inverse followed by phi collapses to a single identity box. The cube root function is absorbed. It never appears as a standalone function subject to differentiation. The remaining chain is identity composed with identity, which collapses again to a single identity map on R. The coordinate representative of F is therefore the identity map, a C-infinity map. C-infinity confirmed. The map F is smooth from R phi to RID. For comparison, the transition map tau 2 from part 2 was the identity composed with phi inverse. Here, the identity sits on the left and phi inverse sits on the right, with no phi to the left of phi inverse to cancel it. Phi inverse sits alone in the tau 2 chain. There is no adjacent phi to absorb it. The cube root remains, and differentiation of the cube root at 0 diverges. The critical difference between the diffeomorphism computation and the transition map computation is entirely one of position, where phi sits relative to phi inverse in the composition. The inverse of F is F inverse equals phi inverse, the map from RID to R phi, sending t to the 1/3. Compute the coordinate representative of F inverse in the reverse direction. The source chart is the identity, which is its own inverse. The target chart is phi. The representative is phi composed with F inverse composed with the identity inverse. Substituting F inverse equals phi inverse, phi composed with phi inverse gives the identity, and composing with the identity inverse on the right changes nothing. The result is the identity map on R. The coordinate representative of F inverse is also the identity map on R, which is C infinity, so F inverse is smooth as well. The box on screen states why this does not contradict part 2. There, the identity sat to the left of phi inverse and left the cube root uncancelled. Here, phi sits to the left of phi inverse instead, and the composition collapses to the identity. The crucial difference is the position of phi relative to phi inverse in the composition, and that position depends entirely on which chart is assigned to which manifold. Both coordinate representatives of phi and of phi inverse reduce to the identity map on R. The proof is complete. The identity map is C infinity, so phi is smooth from R phi to RID, and phi inverse is smooth from RID to R phi. Therefore, phi is a diffeomorphism. The logical situation can be stated sharply. A phi and AID are not equivalent as atlases. Combining them into a single atlas would require the transition map T to the 1/3 to be C infinity at 0, and it is not. On the other hand, R phi and RID are isomorphic as smooth manifolds. The map phi is a diffeomorphism, and verifying its smoothness requires only computing its coordinate representatives within each manifold's own chart. Those computations give the identity. Both facts are true simultaneously. Atlas inequivalence and diffeomorphic equivalence measure different things, and neither implies the negation of the other. Placing our example in its broader mathematical context requires distinguishing non-equivalent structures from the stronger notion of exotic structures. Two terms must be carefully distinguished. A non-equivalent structure is one that cannot be combined with the standard atlas into a single C infinity atlas. That is, its transition maps to the standard charts are not all C infinity. Our example of phi of S equals S cubed is non-equivalent to the standard structure in this sense. An exotic structure is a stronger condition. It is a smooth structure on a manifold that is not diffeomorphic to the standard smooth structure on that manifold. Our example is not exotic. The two manifolds R phi and Ri are diffeomorphic via phi itself. The classification of smooth structures on Euclidean spaces reveals a sharp dimensional dependence. For Rn with n not equal to 4, every C infinity differentiable structure is diffeomorphic to the standard one. This was proved by Stallings in 1962 for dimensions 5 and above, and is classical for dimensions 1 through 3. Dimension 4 is exceptional. Donaldson's work in 1982 and Friedman's work in the same year, taken together, imply the existence of uncountably many pairwise, non-diffeomorphic C infinity structures on R4. These are the so-called exotic R4s. Our one-dimensional example, by contrast, represents the simplest instance of non-equivalent atlases, and the two resulting manifolds are diffeomorphic. With the full solution now in hand, we return to the original problem statement to confirm that every part has been addressed. The problem from Gadea, Munoz Maske, and Mikitiuk asks us to prove something specific. Phi of S equals S cubed defines a C-infinity differentiable structure on R that is different from the usual one given by the identity atlas. The three steps are shown on screen, each tagged with the part that established it. The single chart criterion came from part 1, the failed transition map from part 2, and the diffeomorphism computation from part 3. Assembled together, they answer exactly what the problem asked. Phi of S equals S cubed defines a C-infinity atlas that is inequivalent to the standard one, while still producing a manifold diffeomorphic to R with its usual structure. The problem is completely solved. The central lesson of this video is that two differentiable structures being distinct as atlases does not imply that the resulting smooth manifolds are non-diffeomorphic. In dimensions 1, 2, and 3, every smooth structure on Rn is diffeomorphic to the standard one. Dimension 4 is the unique exceptional case where uncountably many exotic smooth structures on R4 exist, none of them diffeomorphic to the standard structure.